Hello my dear students, today we are going to discuss another chemistry lesson in grade 13 in this Guru Gedara education programs. So, let us see what is the unit that we are supposed to discuss. We are going to discuss unit 11 chemical kinetics. So, let us see the competencies that we are supposed to discuss today. There are three competencies that we are going to discuss. The first one is method to determine order of a reaction. Now, this competency already we had discussed in a previous lesson and we are going to continue that part. Other than that, we are going to discuss how the physical nature and the catalyst will affect reaction rate. So, those are the three competencies that we are going to discuss in today's lesson. So, we will start with the first one, half-life. The standard symbol for the half-life is given here. You can see it is written as T half. The T is in simple letters. And how do we define this? This is defined as the time required to reduce any initial concentration exactly to half. If you are provided with a certain reactant concentration, the time required to reduce that one exactly by half is known as half-life. So, once the reaction is going on, now this half-life is given with respect to a reactant. Once the reaction is going on, what will happen to the concentration of the reactant? Reactants are consumed. Then concentration of the reactant decreases. With the time, concentration of the reactant decreases. Now, already we had discussed order with respect to certain reactant. It does not matter zero order reaction, first order reaction or any other higher order reaction, always reactant concentration decreases with the time. So, then advantage of the half-life is this can be used to get idea about reaction rate. It can be used to get idea about reaction rate. When the reaction is fast, what will happen to the half-life? When the reaction is fast, the reaction proceed within short time period, no? Then half-life will be less. Then the given initial concentration get decreased by half in short time period. The given initial concentration get decreased to half by short time period. So, then time taken to reduce this initial concentration to get decreased by 2 times will be very low. And for a given reaction, what are the factors that affect this half-life? For a given reaction, half-life depends only on the temperature. For a given reaction, half-life depends only on the temperature. What about if you want to compare two reactions? If you want to compare two reactions, then half-life depends on the order of the certain reaction. We came to know if you have several reactants, the order with respect to each can be calculated, then we can find out something called total order. Total order is the summation of orders with respect to each and every reactant. So, depending on that total order, half-life will vary from one reaction to another reaction. And in our syllabus, we are going to discuss how the half-life varies in first order reaction. We are not going to discuss more details about how the half-life varies in other reactions, but we discuss only how this half-life will vary in first order reaction. In first order reaction, the characteristic feature is half-life is a constant. What is the meaning of that? Half-life is a constant mean whatever the given concentration get reduced to half by a certain time period. Now, if you have a different concentration, that also get reduced to half by the same time period. Or in simple word, it does not matter whatever the initial concentration, all the time required to reduce this initial concentration, the given initial concentration to half is a constant. That is the characteristic feature in first order reaction. Now, this you have to memorize. In a first order reaction, half-life is a constant. That means the half-life does not depend on the initial concentration of the reactor. If you are provided with 1 m initial concentration or if you are provided with 5 m initial concentration, in first order reaction all the time required to reduce that exactly to half is a constant. So, here the graph is given for the variation of concentration with time in first order reaction. Now already we came to know half life is a constant. So let's see whether it is a constant or not. To make it easy, here you are provided with certain data in the graph. Now initial concentration is given at this value approximately, let us say it is 1.6. Initial concentration is given as 1.6 mole per decimeter cube. Half from that mean 0.8. This value. The time required to reduce this 1.6 into 0.8 is, can you all identify? The time required to this value is how much? 400 seconds. And let us say the initial concentration is given as 0.8. Initial concentration is given as 0.8. Half from that mean 0.4. This value. So if you want to reduce this 0.8 into 0.4, again we have to spend another 400 seconds. That means if you are provided with 1.6 as the initial concentration, to reduce that into 0.4 altogether we have to spend 2 half life, then total time required to get done this change will be 800 in seconds. The total time required to get done this change will be 800. Now let us say the initial concentration is 0.4. If it is 0.4, half from that mean 0.2. So then time required to reduce 0.4 into 0.2 is again 400 in seconds. So then if the initial concentration is 1.6, then if we need to reduce that concentration into 0.2, that means altogether we have to spend 3 half life, then total required time will be 1200 in seconds. To make it more easy or to make it more clear, I will write it like this. If you are provided with initial concentration as 1.6, half from that mean 0.8. To get done this change, we need to spend 1 half life. How do we write half life? It is written as T half. Then half from 0.8 mean how much? Half from 0.8 mean then 0.4. Then to get done this change, we need to spend another half life. Half from this one mean then 0.2. To get done this change even, we need to spend another half life. Then total time required to get done this change will be, that means if you want to convert 1.6 initial concentration into 0.2, we need to spend 3 into half life. That means the total time will be 1200 in seconds. That is because in first order reaction half life is a constant. When it comes to 0 or second order reaction, half life is not a constant, and we are not going to discuss more details about those in our syllabus. So here you are provided how to get expression for the half life. We came to know it is a constant. Why does it become constant? So this real relationship, how can we obtain this one, is given in this equation. The relationship between initial concentration and any other concentration is given here. The rate constant, K is the rate constant equals this relationship. So if you know this rate constant, half life means the initial concentration has to be reduced by half. This is the initial concentration, it should get reduced by half. Then we call it as, the time is known as T half, and then initial concentration is A naught, then present concentration is known as A naught by 2. The present concentration will be A naught by 2. So then if you simplify this equation, you can get this answer. You will end up with half life equals 2.303 over K, which is our rate constant, into log 2. We know that log 2 is 0.3010. Easily you can find out from a log table. So then multiply 2.303 by this value, you will end up with half life is this one. And in our A level paper, we are asked to find out expression for this half life in first order reaction given this relationship. So let us see how do we prove this relationship when you are provided with this information. So, in the exam this equation is given. You will be provided with 2.303 of the present concentration equals minus K T. What is K? K is our rate constant, T is the time required to get done this change, plus 2.303 log initial concentration of A. If you are provided with the initial concentration of the reactant and present concentration, the time required to reduce initial concentration into the present concentration is T. It is not half-life, it is T. So, if you want to rearrange this expression to half-life, what we have to do? We have to make a small change in this expression. This equation is given in our A-level paper and we are asked to derive relationship for half-life. So, to get half-life in this equation, we have to make a small change in the equation. Let us see what is the equation that we are supposed to make in this expression. Now, half-life is the time required to reduce any initial concentration exactly to half now. So, now I am going to make a small change in this expression. This one we can write as it is. Do not worry about this initial equation. In our A-level paper that will be given. All you need to get expression for the half-life. So, then I will write this as it is. Now, initial concentration is A naught now, half from that mean, then I can write it as A naught by 2. Equal minus K T plus this we can write as it is. Now, what had happened during this is initial concentration get reduced to get reduced by 2 now. So, then time will be the half life. The time required to reduce this given initial concentration to half is known as half life. That is why I had made this change. Now, time is considered as T half, whereas the presentation concentration will be half from the original value. So, then all we need to make a simplification. So, that is your math knowledge. So, let us see how do we simplify this. I will take this part into left side. So, then we can write it like this. And I will take this part into right side. Minus so, then you can see this 2.303 the log value are common. So, then we get A naught. Subtraction mean a division of the two value. So, then I can write it like this. When you simplify, you will end up with 2.303 log 2. Already we came to know log 2 is 0.3010. So, when you simplify this one, you will end up with 0.693. We are asked to get expression for half life. So, then our expression will be half life equals 0.693 over K. So, this is the expression for the half life. What is K? K is our rate constant. So, do not worry about this expression in the exam. Always that expression is given, all you need to derive expression for the half life. The theory part that we should know is the initial concentration is A naught, half from that mean A naught over 2. The time required to get done this change will be T half. Then after that apply your normal maths knowledge and get expression for T half. The same relationship is given by this expression. This is same as the previous one, only difference is instead of the log, here they had used ln. Here they had used something called ln. We call it as natural log. We call it as natural log. It's very familiar for math students, but bio students, do not worry about that one. I will tell how to get the relationship, because in our new syllabus, in some of the mathematical expressions they use this natural log or ln. So, let us see again how do we derive expression for the half life. Here you can see half life is given in this expression. So, then we can write, again do not worry about this expression. In the exam this first equation will be given. All you need to apply your maths knowledge and simplify to get expression for half life. So, then again we are going to make a small rearrangement in the equation. Our initial concentration is A naught. Half from that means, then I could have rearranged this as A naught over 2 equal. Now, time is half life. The time required to reduce initial concentration exactly to half is T half. So, then again let us take this part into left side and this part into other side. So, now you can see ln is common. Subtraction means the division of log. So, this we can write as ln 2, then half life equals ln 2 over k. That is how you get that expression. The relationship between natural log and log is so, then we can substitute that one here. You can see you will end up with the same expression, because log 2 is equal 0.3010 over k. So, we get the same expression as earlier. So, in the exam do not worry whether it is given in the form of log version or in the form of ln version. You need to apply your basic maths knowledge to get expression for the half life. One of the advantage of this half life is carbon dating. That means we can use this one to find out the time of age of fossils. So, carbon 14, carbon has several isotopes, carbon 12 is there, carbon 13 is there, carbon 14 is there. Out of these three, carbon 14 is the radioactive isotope. So, in the atmosphere you get certain amount of carbon 14 radioactive isotope. So, that carbon 14 can be converted to carbon dioxide in the atmosphere, and then it is absorbed by plant to make glucose or any other plant food. And once the plant die, this carbon 14 does not replenish to the atmosphere, instead it will decay. That means it will come to a certain situation which is stable isotope by emitting beta particles. So, then this decaying process, decaying of C14 is first order reaction. Now, already we came to know in first order reaction half life is a constant. That means the concentration of C14 to get reduced exactly by half is a constant value. The time required to get done this change is a constant value. Approximately, that is 5700 years. The time required to reduce initial concentration of C14 concentration to half is a constant, which is 5700 years. So, then the graph is given how the concentration of C14 varies with the time. So, as it is a constant, then depending on the present C14 percentage in the given fossil sample, the age can be determined. So, this is really important aspect of half-life. So, here you can see how this C14 isotope can pass through plant and then through animals. You will learn more details about this course in biology, but in chemistry we do not want to know that much details, but you should know it as one of the important aspect of this half-life. So, let us see how do we do calculations based on half-life. Now, here you are provided with a very simple question. You are provided with radioactive isotope, certain radioactive isotope. Its initial mass is given as 24 grams. The initial mass is given as 24 grams and it should get reduced to 6 grams over a period of 60 days. It get reduced to 6 grams by a certain 60 days. So, then this reaction, radioactive decaying of isotope is a first order one. Let us see how do we do the question. Initial mass is given as 24 grams. Half from that means the decaying of radioactive isotope is a first order reaction. In this question it is not given as first order because all we know that decaying of radioactive isotope is a first order one. That is why it is not given. Otherwise in the exam they should have mentioned whether the given reaction is first order or not to find out half-life. Without knowing that we can't calculate half-life. Now, initial concentration is given as 24, half from that means 12, half from this 12 means 6. Then to get done this change altogether, we need to spend 2 half-life. I will write it like this, then it will be more clear for you. Initial concentration is given as 24 grams, half from this one means 12 grams. To get done this change, we need to spend 1 half-life, that is because it is a first order reaction. In first order reaction, half-life is a constant. Half from this 12 means, if the initial amount is 12, half from that one means 6 grams. Then to get done this change, again we have to spend another half-life. We have to spend another half-life. Then to convert this 24 grams to 6 grams, altogether we need to spend 2 half-life now, 2 half-life. The total required time is given as 60 days, total required time is given as 60 days. So, then I could write 2 half-life equals 60, then half-life equals 30 days. The half-life can be expressed in days or years or in seconds or in minutes. In that carbon 14 dating we came to know it is years, it is given in years, 5700 approximately in years. Now, here this one is given in days. So, half-life of this reaction will be 30 days. So, here you are provided with another reaction. The importance, another question, the importance of the question is it is given as first order. The calculation can be done like this, that is because the reaction is first order. Otherwise, if the order with respect to that particular reactant is not given, you can't do the calculation. And the first part, they had given the half-life, it is given as 20 minutes. So, in this question half-life is given in minutes. Calculate rate constant K, simple K. We know that it is rate constant, you are asked to calculate the rate constant, and in the second part you are asked to find out the time required to complete the reaction by 75%. The time required to complete the reaction by 75%. So, let us see how do we do this. So, in this first order reaction, can you all remember already we derived this expression, half-life equals 0.693 over K. It is better if you can remember this equation, otherwise you have to spend more time to get the answer. So, K is our rate constant, directly rate constant can be calculated simply by applying the given value. So, then 0.693 over the half-life. You can substitute the half-life in minutes as it is, or if you want you can convert that into seconds. If you substitute that in minutes, the answer will be this one. If you substitute the answer in seconds, then you need to divide this one by 60. And in the exam, you can keep the answer in half-life you can substitute the half life in whatever the given unit, no need to make a unit conversion unless they specify. So, that is our first part. We are asked to calculate rate constant, simply we need to substitute the half life. Now, the second part, we need to complete the reaction by 75%. We need to complete the reaction by 75%. Then the remaining amount of the reactant will be how much? The remaining amount of reactant will be 25. So, let us say initial concentration is 100, half from that one mean 50 now. Then we have to spend 1 half life. Half from, if the initial concentration is 50, half from that one mean 25. So, then the remaining part, once this conversion is over, the remaining part is 25 if the initial amount is 100%, initial amount is 100. So, then we have to spend another half life. So, to get down this total change, if you want to complete the reaction by 75%, the remaining amount will be 25. So, then we have to spend altogether 2 half life. We have to spend altogether 2 half life. So, as it is a first order reaction, we have to spend 2 half life now. Then half life was given as 20. Then what is the total required time? Total required time in this one will be 40 minutes. The half life is 20. To get done this change, we have to spend 2 half life. Then total time required will be 40 minutes. Then here we are asked to show to complete the reaction by 99.9%. Whenever you want to complete a first order reaction by 99.9%, the time required to spend is 10 times from the half life. Let us see how do we do this calculation. So, the initial amount is given as 100, half from that means 50. To get done this change, we need to spend 1 half life now. Half from this one means then 25. We have to spend another half life. The calculation can be done like this, that is because half life is a constant. They had mentioned it is a first order reaction, one of the most important thing in the question. Without giving this order, we can't do the calculation like this. Half from this one means then 12.5 now. We have to spend another half life. Half from this one means 6.25. We have to spend another half life. So, like that the process has to be continued like this. Now, this we need to divide by, this answer has to be divided by 2, that means altogether by 4. This initial concentration also has to be reduced by 2. This has to be reduced by 2, even this has to be reduced by 2. So, you will end up with, if the initial amount is 0, the remaining amount will be 0.1%. So, to get done this change, we have to spend altogether how many half life? Just calculate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Altogether we have to spend 10 times from the half life. So, then if you know the half life, the corresponding time can be calculated. There is a equation which gives the relationship between the initial concentration and time required to get done the change in the reaction. But it is not necessary to know that equation in our syllabus, simply it is enough to do calculation like this. If the initial concentration is 100, to complete the reaction by 99.9% mean you have only 0.1% left over in the medium. So, to get done this total change, altogether we need to spend 10 times as half life. So, if you know the half life, the total time required for the completion of reaction can be calculated. So, let us see some simple questions that we get in our paper. The same thing is again given here. I told that there is a relationship which gives the time required to get done this change can be calculated. So, here you are provided that again the same thing, the initial concentration is 100%, then to complete the reaction by 99.9%. So, then required half life altogether will be 10 times. No? So, it can be calculated like this. So, you can see we need to spend altogether 10 half life. So, then the remaining amount will be this much. So, then we are going to discuss our second competency in this today's lesson, that is effect of physical state on the reaction rate. The physical state, you can call it as physical state or the contact surface area, actually both will affect the reaction rate. So, this is about physical state of the reaction, reactant. Now, at the beginning of this chemical kinetic, we came to know the reaction can proceed in solid state or can proceed in gaseous state, in liquid state or in aqueous medium. All the time reactions which proceed in solid states are very low. What can be the reason? In solid state, the reaction rate is low because total collisions that occur in the medium will be very low. Can you all remember, in a previous lesson we discussed how a reaction proceed. To proceed any chemical reaction, we came to know there are 3 requirements to complete. As long as the 3 requirements are completed, then only the reaction can occur. What are those 3 requirements? The 3 requirements are, first of all, reactant molecules should colloid with each other. Secondly, they have to colloid with certain specific orientation. And thirdly, the kinetic energy of the colloiding molecule should be greater than a certain minimum value, which we call as activation energy. The 3 requirements to get done any chemical reaction are, the reactant molecules should colloid with each other, they have to colloid with certain specific orientation, and kinetic energy of the reactant molecule should be greater than a certain minimum value, which we call as activation energy. So, in the solid state, the total collision occurs in the medium will be very low. If the total collision rate in the medium is low, reaction rate will be very low. Then solid state reactions are having the slowest rate. When it comes to gas phase or liquid phase reaction, they are fast. The reason is, in gas phase or in liquid medium or in the aqueous medium, the total collision can be larger. The total collision occurs in the medium will be larger. And this factor, the physical state, is also important in gaseous reactions. We call this as heterogeneous reaction. Now, these 2 terms also we had discussed in a previous lessons. Heterogeneous reaction means the reaction will occur in a different physical state. The reaction will occur in a different physical state. The reactants are at different physical state. So, if you have different physical state containing reactions, then the reaction rate depend on the physical nature of the contact surface area of the reactant. This is more suitable to apply whenever you have a solid reactant. If you have a solid reactant and a gaseous reactant, then reaction rate depend on the contact surface area of the solid reactant. I told this is important in heterogeneous reaction. That means one of the reactant will be at a different physical state, another reactant will be at a different physical state. You can consider any combination, but in our A-level syllabus we are focusing about reactions which has one solid state reactant. So, then the whole reaction will take place on the surface of that solid. So, then higher the contact surface area of the solid, the reaction will be faster. Let us see what is the reason to increase the rate when you have higher contact surface area. How do we increase the contact surface area? The contact surface area of a solid can be increased by introducing that in a powdered form. The solid can be used as a lump or solid can be used as a powder. When you convert the lump into a powder, contact surface area of that solid get increased. contact surface area of the solid get increased. So, if the contact surface area is high, you get more frequent collisions on that, then reaction rate increases. So, then all the time whenever we have the reactant, solid reactant in the powdered form and in the lump form, the powder will offer higher reaction rate. The powder will offer high reaction rate. Here you can see in the diagram, when it is small, when the particle size is small, the contact surface area is high. In this large cube, you can see the surface volume ratio is 2. In this small cube, you can see the surface volume ratio is 6. So, then smaller the size of the particle, contact surface area increases. That is why it is necessary to introduce the solid reactant in powdered form to get done the reaction fast. Then another important factor that affect reaction rate, this is our last competency that we are going to discuss today, that is the effect of the catalyst. In most of the reactions, reaction rate can be increased by adding a catalyst, but make sure the added substance will act as catalyst for that particular reaction. You can't use the same substance for all the reaction as catalyst. Depending on the reaction, the catalyst will be specific. So, what is catalyst? Catalyst is a substance which increase the reaction rate. All the time it will increase the reaction rate without undergoing any chemical change, Now, how it can improve the reaction rate? The rate can be improved by providing alternative path for the reaction. The reaction proceed in a certain mechanism. When you introduce the catalyst, path or the mechanism will vary. Not only that, it does not give a normal, different or new mechanism, it will provide a mechanism where activation energy is lower than the previous situation. It will provide a new path where activation energy is lower than previous situation. In such kind of situation, the total collisions occur in the medium will be high, because fraction of molecules with activation energy or more than that get increased, then reaction rate increases. The advantage of having catalyst in the reaction is the rate can be increased at the same temperature. One of the most important aspect in our reaction rate is to have higher rate in industrial wise. In industry, we need to get done the reaction within short time period to reduce the production cost. So, this can be done by two ways. You can increase the temperature to increase reaction rate, or you can add a catalyst. The problem with high temperature is to provide high temperature to increase the reaction rate at high temperature, we have to provide again energy, we have to spend more energy, which is again expensive. So, rather than going for that expensive method, in industrial wise, simply the reaction rate can be increased by introducing catalyst to the medium. So, what kind of reaction is this? The diagram clearly gives what will happen in the presence of a catalyst. The red color line is in the presence of catalyst and the black color line is without the catalyst. The red color line gives what will happen to the mechanism in the presence of catalyst. Shall I mark it to make more clear? This one is with catalyst. The given reaction is that going to be exothermic reaction or endothermic reaction? Can you all identify this one? Products are having more energy than reactants. When products are having more energy than reactant, to reach up to this position, the extra energy has to be absorbed from the environment. Therefore, this reaction is endothermic reaction. Products are having more energy than reactant. To convert reactant into products, extra energy has to be absorbed from the environment. Whenever it is absorbed from the environment, the process is known as endothermic. You can use catalyst even in endothermic reaction. When we apply the catalyst, the reaction will proceed in a different mechanism where activation energy is lower than the previous one. So, then the rate will be faster. What about this diagram? Can you all identify this diagram? Now, here reactants are having more energy than product. Reactants are having more energy than product. Again, the red color one give how the reaction proceed in the presence of catalyst. The red color one gives how the reaction proceed in the presence of catalyst. As reactants are having more energy than product, we call this as exothermic reaction. Reactants are having more energy than product. So, when reactants are converted to product, the extra energy of the reactant is released to the environment. When it is released to the environment, we call it as exothermic reaction. So, we can use catalyst in exothermic reaction even. So, what we need to consider here is, it does not matter whether the reaction is exothermic or endothermic, we can use the catalyst. And what about the enthalpy change? When we add the catalyst, does it change? This is the enthalpy change of the reaction. Even in the presence of catalyst, still we have same enthalpy change. So, one special feature or the characteristic in the catalyst does not vary the enthalpy, magnitude of the enthalpy and sign of the enthalpy. Sometimes students get confused that when we use a catalyst along with endothermic reaction, they think that the reaction is converted to exothermic one, which is not correct. If it is a exothermic reaction or endothermic reaction, when you add the catalyst, the rate can be increased, but the magnitude of the enthalpy change or the sign of the enthalpy change do not vary. So, we came to know when we add the catalyst, it will provide a new path which consists a lower activation energy. Now, if it has lower activation energy, what will happen to the reaction molecules? Then total number of reactant molecules which has activation energy or more than that get increased. We came to know to proceed any reaction, one of the most important requirement that has to be completed is the total molecules with activation energy or more than that has to be high. To get done the reaction, total number of reactant molecules with activation energy or more than that has to be high. When we add the catalyst, the activation energy get decreased, then the total number of molecules, it is better to use the term fraction of molecules with activation energy or more than that get increased. So, if it get increased, then total collisions in the medium get increased. Out of these total collisions, some of them can be effective collisions, then effective collision rate get increased in the presence of catalyst. So, then reaction rate increases. Clearly, you can understand this by the diagram. Now, this is one of the well known graph in gas laws. We call it as Maxwell-Boltzmann distribution curve, which gives the variation of energy or the speed of the molecules. Then with the catalyst, you can see the activation energy is given. The blue color one EA is the activation energy in the presence of catalyst, and the red color EA is the activation energy without the catalyst. You can see toward this direction only energy get increased, but if you have catalyst, the activation energy get decreased, which is a lower value. This value is a lower value than this one. So, when you have the catalyst, the total molecules with activation energy or more than that will be high. That is the colored area in the graph. In the presence of catalyst, we get all together this much of molecules which consists activation energy or more than that. As it get increased, the total collision rate get increased, then probability to have effective collisions also get increased, then reaction rate increases. Now, these catalysts can be classified into several categories. The first one, homogeneous catalyst. In homogeneous catalyst, the catalyst and the reactants are at the same physical state. Clearly, you can see I had taken one of the well known reaction in our syllabus, that is hydrolysis of the ester. Here dilute sulfuric acid is used as the catalyst. So, then catalyst is also aqueous, our reactant also aqueous. Catalyst and the reactants are at same physical state. The next type of catalyst, heterogeneous catalyst. In heterogeneous catalyst, the catalyst and the reactants are at different physical state. When it is different physical state, you can consider any combination, but this one is characteristic for gas phase reactions. What are gas phase reactions? The whole reaction occurs at gas phase. Reactants are gases, products are gases, but the catalyst is in most of the cases will be a solid. That is the characteristic feature in heterogeneous catalyst. In most of the gas phase reaction, we use solid substance as a catalyst. One simple example, again well known equation in our syllabus, chemical reaction in the Haber process. Here the reaction is a gas phase one, reactants as well as products are gases, and iron metal iron is used as the catalyst, which is a solid. Third type of catalyst, we call it as self catalyst. Self catalyst is something special, we call it as one of the product. One of the product in the medium can act as catalyst. Once the reaction is going on, we get more and more product. When we get more and more product, as the product can act as catalyst, rate get increased. Normally with the time, reaction rate get decreased, but in this kind of reaction, as you are getting product which act as catalyst, with the time reaction rate increases. This example is not common in our syllabus, that is the thermal decomposition of arsine hydride of the arsenic. Here formed arsenic can act as the catalyst, then when you get more and more arsenic, the reaction rate increases. That is because arsenic will act as the catalyst for this reaction. We call it as self catalyst or auto catalyst. The last type of the catalyst, it is enzyme. Enzymes are also catalysts which can increase the reaction in biological cell. They can increase the reaction rate in a living cell. We call these as biological catalysts. The characteristic feature of enzyme is those are very specific, unlike normal chemical catalyst. And what are inhibitors? Inhibitors are known as substances which decrease the reaction rate. Inhibitors are the substances which decrease the reaction rate. We are not going to discuss more about inhibitors in our syllabus. All you need to know that they will reduce the reaction rate unlike catalysts. So, that is all about the today's lesson. So, here in this lesson we discussed so many new terms. We came to know what is half life. You should know how to define half life, and also you should know that in first order reaction half life is a constant. In first order reaction half life is a constant. Half life is given by 0.693 over k, which is our rate constant. And I had mentioned how to derive that equation considering the log expression as well as ln expression. Do not worry about how to get that expression. All you need to know to apply your maths knowledge to get expression for the T half or the half life. Then we should know how the physical state of a reactant will affect on the reaction rate. You should know the physical state as well as contact surface area, both will affect the reaction rate, and you should know to explain how it will affect. And thirdly, our third competency was we should know how to explain the effect of the catalyst in chemical reaction, and also you need to have little bit idea about the classification of catalyst, and you should be able to identify what will happen to the energy profile in exothermic reactions and in endothermic reactions when you add the catalyst, and also you should be able to explain how the activation energy has to be marked in Maxwell-Boltzmann distribution when you use a catalyst in a chemical reaction. So, that is all about the today's lesson. You can get more information about these things when you go through the resource book in resource books published by NIE. You can freely download these books. So, go through these books, you can get more information and more examples about this theory part, and also you can watch all these lessons, the previous lessons in chemical kinetics in YouTube channel NIE. So, let us see more details about the remaining theory part in future lessons. That is all about today's lesson. Thank you.